Sorry, that took a little bit longer. We're gonna start by going over the work we did on Friday. I know I helped a whole bunch of you, but I definitely saw a few very common mistakes throughout the day that I do want to make sure we talk about. Just to get an idea, again, like I've mentioned before, or like we've even done before, since the first one was multiple choice, which answer was it? Oh, 1, 2, 3, 4. Sorry, that's what I meant. Show me what you get. So 1, 2, 3, or 4. Should be 2. So just because I saw some wrong answers, remember the formula we're using is the change divided by the time it takes for that change to happen. So how do we figure out the change? The top number. We do subtract. So it says the temperature of the water in the container was 60. 10 minutes later, the water temperature was 35. So we start at 60. We go to 35, which, by the way, when you subtract those, what do you get? 25 degrees. How long did that change take? Or 10 minutes. So 10 minutes, 10 minutes. Notice that they had 25 degrees as an answer. Remember when I said the region people are big old jerk faces? They absolutely are for this reason exactly. Yeah, the temperature did change 25 degrees, but that's not the rate of change. That would, but look, they even put it first. They even put it there, so you saw it, and you didn't even look at the rest of the answers. Look how much different the rest of the answers are. When you do 25 divided by 10, you should have gotten 2.5 degrees per minute. Now, question 2 is slightly different because instead of just flat out saying it in a sentence that it started at 60, ended at 35, and it took 10 minutes, they gave you a graph and they told you to basically do it from there. So we need, again, from, according to the reading, 6 a.m. and noon. So here is the temperature at 6 a.m. Here is the temperature at noon. So how much did it change going from 6 a.m. to noon? So 6 a.m. the temperature was 30. Noon, looks like it was a little below 58. So we'll go with 48. How much did it change? How much does it change? 18 degrees. 18 degrees is how much it changed. How long did it take for that change to happen? There's that 6 hours. So how much, what is the rate of change? What was it? 3 degrees per hour. Ooh, did we read it wrong? Did the total, you did 4 at 18, you mean? Yep. And again, notice they gave you what they expected you to screw up. So they catch everybody, they know the common mistakes, and they make those answers. So you do have to make sure you use the formula. Being able to read graphs is important. According to this, A, B, C, or D, which one does the temperature increase most rapidly? Would you say A, B, C, or D? So 1, 2, 3, or 4. Yeah, that is answer A. How do you know, by the way? Not necessarily because it's the highest up. I know what you mean, but you're using the wrong word. Yes, you guys might want to add that. This one has the steepest slope. That means that it changes really rapidly. Every minute that temperature increases a lot more. Which one's not a constant rate? A, B, C, or D? 1, 2, 3, or 4? Yep, I'm seeing mostly B's. How do you know, by the way, that it's not a constant? Okay, yep, it's not a smooth line, I guess we'll say. I don't want to say straight because I don't know if you guys will think of straight as either straight across or straight up and down. But again, notice these guys all have nice diagonal lines. This one goes diagonal, flat, and then diagonal again. Question 5, I can guarantee you if this was a Regents question, it would have had a follow-up and it would have said, include the correct units. So before we even get started, I want you guys to look, do you even have units listed there? Some of you did, a lot of you did not. If you did not, you have to make sure you do. And even those of you who did, let's make sure that they were right. So once again, this same formula got used. It was the change divided by the time. Now, a lot of people had trouble trying to figure out the change for this one. In this case, it was a hurricane that was moving across the state or the country. So we're really looking for its change in location. According to the reading, how much did its location change? 2,600 kilometers. That means it moved 2,600 kilometers. And how long did it take for that movement to happen? 4 days. Now, I did see some people trying to change that 4 days into hours. You don't need to do that. The directions did say the daily rate of change. If you did change it into hours, I don't think the Regents would mark you wrong as long as you did it correctly and labeled it correctly then. By the way, I think I saw most of you had 650, right? What are the proper units on that? So teachable moment, because I have a feeling a bunch of you got the wrong units. What'd you try? Okay, anybody have anything different as your units? All right, that is correct. It is kilometers per day. Now let me just show you where that comes from. So just like we took 2,600 and divided it by 4, you do the same deal with the units. We try to take kilometers and divide them into days. Do kilometers and days go together? Like, can you simplify kilometers and days? No. So you leave them flat out like that. Now I do it the side slash, but if you did you kilometers over days, this is perfectly fine as well. So this means this hurricane traveled 650 kilometers per day. Now about the abbreviations, I saw a bunch of crazy abbreviations here. If you are not sure how to properly abbreviate a number such as kilometers, by the way, this is the only acceptable abbreviation for kilometers. So I saw a bunch of you doing like kilo, K-I-L-L-O maybe. I don't know if there's 2 L's. Anyway, doesn't matter. This is the only acceptable way to abbreviate kilometers. If you're never sure, if you're ever not positive how to abbreviate it, don't. So it could have also been written out kilometers, the word, per day. And day doesn't have an abbreviation, so don't do just a D there. That's something different. Questions with any of that? All right, this one tricked up a bunch of people because it was just a data table. And they asked again, what is the average rate of cooling for the water in the beaker? We see it started off at 0 minutes at 90 degrees. And after 8 minutes, it cooled to 54. How do we figure out that change in the rate of change, I should say? What over what? How do we find the top number? What? How do we, yeah. 90 minus 54, which gives you, oh shoot, did anybody write it down? 90 minus 54 is 36. 36, and we divide that by how long did it take? Good. I saw some people doing 9 because there was 1, 2, 3, 4, 5, 6, 7, 8, 9 boxes, but that's a total of 8 minutes. So we do 36 divided by 8 minutes, and hopefully you got answer 3, 4.5. Now I screwed up and doubled up the next question was the same as on the previous page, so hopefully you saw that that was answer 2. Now, question 8. There were multiple things you had to do there. First, you had to do a scale, then you had to plot it, then you had to connect, and over here you had to find the average rate of change. Hopefully your graph looks something like mine. So it went up. First it was flat, then it went up, flat again, flat again, up again. So answering question A, how do I determine the rate of change for this, the average rate of change? Again, it's still the same formula. Rate of change equals the change divided by time. How much did the temperature change in this experiment? 10 degrees. How long did it take? 10 minutes. That is 1. Again, you have to have the correct units. 1 degree Celsius per minute. And no, this should not have been a constant change. And the reason we know that is it's not one solid smooth line. Or in my case, I said the line is not steady. Question? I know you guys knocked out these first 2 density questions on page 14. If we cut a block in half or in 8 identical pieces, each piece would have the same density as their original, and 3 different samples of the same uniform substance would have the same density. So that is 3 and 2 so far. This one screwed up a whole bunch of you throughout the day. I think I caught everybody's mistakes you were making. But you right off the bat went to do the density of the bar and you're like, I got this. Density equals mass over volume, but there's no mass and there's no volume. So then a whole bunch of people tried to use the magic triangle. By the way, what goes on top for the magic triangle? Mass. M always goes on top. But we don't know the density still. What's the density of the bar and how do you know? What? Same uniform material, so they all have the same density. So you could have done D equals M over V for this cylinder and done 60 divided by 20. Hey, by the way, what is 60 divided by 20? No, it's not. 60 divided by 2 is 30. That was, thank you. I paid these guys to do that mistake for me because that's what I wanted to prove to you. You guys know 60 divided by 20 is not 30. But when we do math that we're used to doing since we were little kids in our head, that's when you screw up. Please don't do math in your head. Use a calculator. Don't try to rush it. 60 divided by 20, that is 3. So if the density of the cylinder is 3, what's the density of the bar? 3. And which graph looks correct? 8, 1, 2, 3, or 4, please. It is, they're all the same. Now we have to use the magic triangle to find the mass of the bar. According to the magic triangle, mass, cover up the M, you're left with D next to B. That means multiply. So you take our density, which we know was 3, the volume, which is 30, and you get 90. Now, same deal for the volume of the sphere. Cover up the V, you're left with M over D. And so in that case, we're taking 75 divided by 3, and you should get 25. And when you cut these in half, density will stay the same. And again, density will stay the same. Did you ace it? Ish. There were 19 questions, so if there was 20, each question would have been worth 5 points. Would you have been happy with your grade? Okay, so a few things that you might have saw that you were making mistakes on, but hopefully not too many. So we're gonna move on to page 16 and take a look at the title of page 16. change in density. Didn't we just spend all of Thursday and most of Friday talking about how density doesn't change? Okay, so again, when does density not change? When you split it, and it doesn't have to just be half, it could be you split it into gazillion pieces. Each piece would have the same density as the original. You could split it into two pieces. One could be the size of a basketball, and the other could be the size of your fingernail. The density of those pieces is still the same no matter what, because it's still made out of the same thing. So density doesn't change when you cut something, but density does change sometimes. Can you guys think of any time when you could make density change? And again, remember, wait, let's go back. What's the definition of density? Good, I love it. If you don't remember, flip back, what is it, 2 pages, 3 pages? You don't know something when I ask, that's really good practice to just flip back and check. What is it, Drake?
Oh, I was saying that to change your density.
No, hang on, we're first getting, what is density? Crisanto?
The amount of matter in space.
That is true, so the amount of matter in space, but is there an easier way of remembering? Huh? It isn't a specific volume, that doesn't sound easier to me though. Math? How tightly packed it's really how tightly packed the atoms are inside of an object. So I just rewrote it there. So we want to change the density, change how tightly packed they are. Either make them more tightly packed or looser. And Drake, you knew there's one?
Yeah, melting of metal.
Oh, I couldn't hear you.
Melting.
Melting. So what are we doing when we're melting something?
We heat it up.
We're changing the temperature. You got it. So one thing, our temperature. So temperature, we can change the temperature and that will change the density. Can you think of something else that we could do to an object to make it more tightly packed, make the molecules inside it more tightly packed? Put on some pressure. Or remove some pressure if it's already tightly packed. So if we change the temperature or we change the density, we can, no, I'm sorry. If we change the temperature or we change the pressure, we can change the density. So temperature, you guys know a little bit about temperature. You guys ever, I know I've never been in a hot air balloon. Has anybody here been in a hot air balloon? For real? Was it so cool? Or was it terrifying? I don't know if I could do it, but you guys all understand the basic concepts of a hot air balloon? What causes that hot air balloon to go up? What? We're gonna stop using the word weight and you like weight. We're gonna use not lighter, but less dense. Why is it less dense in a hot air balloon? Because of the temperature. What do you guys know? Warm air. Warm air is less dense, and where's it go? Everybody knows warm air goes up. You guys got any good examples of warm air going up besides a hot air balloon? Yes, those those paper, I think they're called Chinese lanterns, I'm not sure. We've let them go on like the 4th of July. What do you do to let what happens with them? There's a little tiny candle and then it's very light paper and you light it and the air inside the lantern gets hot and it goes up. Desi, got another one or no? Anybody else think of another example when warm air rises? Where's this? Yeah, Scott?
Like the attic being very warm.
100%. If you guys have ever been in an attic of your house, it's hot as bejesus in there. And that's because the warm air rises. Even just the top bunk of a bunk bed is going to be warmer than the bottom bunk of a bunk bed. What about smoke from a campfire? Where does it go? Besides in your face, but it goes up and then in your face. So yeah, smoke also rises. So that's what we're gonna do here. So as temperature increases, the molecules actually move apart. I use my students as a good example of this. Matt, you guys just did the pacer test, right? In gym class? I've seen a whole bunch of you coming to class a little hot and sweaty. When you're all hot and sweaty, what do you want to do with the people around you besides punch them in the face? Do you like being close to people when you're hot and sweaty? No. So just like people, molecules, when they get hot, they need room. They need room. They need breathing room. So just like hot, sweaty people, hot, sweaty molecules, they spread out. And that's exactly how they work on those lanterns. That's how they work on the hot air balloons, is the molecules are spreading out in every direction and they're becoming less dense. So to fill this in, so warm air rises, which you guys already knew, but you might not have realized it's rising because it is less dense. And a good example of this would be a hot air balloon. So what do we end up controlling in a hot air balloon or in those lanterns? Do we control the temperature or do we control the density? We control the temperature, right? We either have it cold, not on the fire, or we make it hot by putting it on fire. And that in turn will change the density. So which way is this graph going to go? As temperature increases, what happens to density? It does decrease. So that's going to look like this. How do we put this in words from the other day? As, which one goes first, temperature or density? As temperature, and what happens to the x-axis? It always increases. I don't know why I just wrote goes up, but I'm going to stick with it. So you can do as temperature increases or as temperature goes up. What happened? Then we read the y, so density. And we already established that decreases. So Drake already mentioned we could melt a metal. When you melt a metal, when we change, by the way, that's because phases matter. If you don't know that phases are solid, liquid, or gas, if you already knew that, you don't have to add that. Which one of those will have the least amount of density? Actually, let's go with which one is the most dense for most objects? Solid, liquids, or gases? Heard most of you say solids. That is true. Think of melting a metal like Drake mentioned. You have a nice solid metal. What happens to that solid metal when it melts? It turns into liquid, and where it could go from being a nice little block. What would happen if this was metal and I melted it? It would spread out. By definition, when something spreads out, is it more or less dense? Less dense. So as it goes from a solid to a liquid, and then if it was to get hot enough, those molecules would spread out even more. For almost every material, solids are the most dense, except for ice. That is the only time. So the only exception to this is water. Water's weird. First of all, if I was to put ice cubes in a drink, where does the ice go? Just one ice cube in a cup of water. Goes in, but it does melt, but I heard somebody say, does it float or sink? It floats. The exception of this is water, because when water freezes, it expands. Water is the only material that does this. It's an exception to the rule. That's the reason you know it happens is because ice floats. That means ice is less dense. You guys also know what happens when you put a water bottle in the freezer. it could explode, or if it's a nice plastic one, it's going to pop out those ridges and things like that. Because water expands when it freezes. So water actually has its greatest its greatest density at 3.98 degrees Celsius. Does that sound like a fact you need to memorize in everyday life? Nope, not unless you're going on Jeopardy. There is, on your front cover, right here, this density, so it's in the properties of water, has a density of 3.98 degrees. Sorry, at 3.98 degrees, that's when it has a density of exactly 1 degree per gram. Sorry, not 1 degree, 1 gram per milliliter. I think you've memorized the rest of this. If a water object floats in water, is it more or less dense? If it floats, it's less dense, and if it sinks, more dense. All right, this bottom of the page is all we got left for today, and then you can start your homework. Pressure. Can you guys imagine a pile of snow in your hand? I know it's rough because it is unfortunately 78 degrees today. You guys are so lucky to be in air conditioning. My kids are whining and crying and moping because they're in a hot, sweaty school and they just want to wear their fall clothes. But anyway, can you imagine a pile of snow in your hand? Is it very dense when it's just in your hand? You're right, it does depend. Can you make it more dense? What would you do? Oh, a whole bunch of you just did it. You're going to squish it into a snowball. Pat that snowball as hard as you can make it. You have just done what to that snowball? You have made it dense, more dense, you're right. You put pressure on it is what I was getting at. So when you put pressure on any object, what's going to happen to those individual pieces? They're going to get squished together and become more dense. So how can we say that? What's the graph going to look like? As pressure, this is always going to increase. The more pressure I put on that snowball, what's going to happen to the density of the snowball? It's going to increase. So is that up line or a down line? Up. And to word that as pressure increases, I'm just going to use an arrow. You think you know what that means? What happens to density? Density also increases. You do have homework. I'm sorry I did not write it on the board yet. We are going to do, I think 6 questions sounds good. You got 6 questions here. I do see that the page number is cut off here. If you want to add the page number, that's page 17 on the bottom. So your homework is page 17. Anybody got questions about that? Sorry, I didn't write it. You still have 5 minutes to do 6 questions. I have a feeling you could probably get it done. Read it, try, put in the effort, make sure you understand this before you leave.